Hi, and welcome to Calculus. We are going to learn about limits and their properties, infinite limits, and limits at infinity today. We will start with limit laws or properties of limits. We have a lot of mathematical symbols going on here. Hopefully these are becoming a little bit more familiar for you, but I will help you work through these. So we are going to let B and C be real numbers. So when you see B and you see C, you need to be thinking that's actually like a number 5 or a 2 or something like that. And we're also going to let N be a positive integer. So integer meaning not a decimal, not a fraction that doesn't, come out to a whole number, or a negative number is fine. Oh, but no, we're doing a positive integer, so positive numbers. And let f and g be functions with the following limits. The limit as x approaches c, remember c is a number, of our function f of x is equal to L, and the limit as x approaches c of f of x, g of x is equal to k. For each of the following examples, we're going to say that the limit as x is approaching approaching c of f of x is 4, and the limit as x is approaching c of g of x is equal to negative 5. So we're going to look at what the name of the law is. You could also call it a property. We're going to look at how it is read in symbols, which I know for some of you is readily understandable, and for others it's a little bit more of a struggle. But the only way we're going to get better at reading the symbols is to expose ourselves to them. And then we're going to apply it in an example. And the example is probably what's going to bring it home so that you actually understand what's going on when you actually put the numbers in the place. So our first law is called the Scalar Multiple Law, or property. And this one says that if I have the limit as x is approaching some number c of b times my function f of x, I can take this b scalar multiple out in front of the limit, go ahead and work the limit out of the function, and then get the answer, L, to that limit problem, and then just multiply the answer, L, times that b. So here's what that looks like with actual numbers. If I'm doing the limit as x is approaching c of negative 3 times g of x, I can say, well, what is the limit as x is approaching c of g of x, just g of x? It's negative 5. So I'm going to take my negative 3 and just multiply it times my negative 5, which gives me 15. You might say, Mrs. Heiss, that's a whole lot of reading just to say negative 3 times negative 5 is 15. Yes, I agree. I think once you get used to these limit properties, you will find that they're pretty intuitive. Might I even say easy? I hope so. We'll see. Okay, the next one is the sum or difference law or property. So limit as x approaches c of the function f of x plus the function g of x, or it could be minus the function g of x. It wouldn't be both at the same time. They're just saying this limit works whether it's a plus or a minus there. Is equal to the limit as x approaches c of f of x plus, or again, minus also works, the limit as x approaches c of g of x, which means that answer L plus or minus that answer k. So here's our example problem. Find the limit as x is approaching c of f of x plus g of x. So we're going to say, what's the limit of f of x when x is approaching c? Well, it's 4. And then we're going to take that sign plus. What is the limit as x is approaching c of our function g of x? Well, it's equal to negative 5. What do you get if you add 4 and negative 5? Well, that's negative 1. So that's the answer. So these little limit answers are pretty much used all throughout each of these examples. We need to reference those. Okay, the next one is the product rule for limits. The limit as x approaches c of f of x times g of x is the same thing as just taking the limit as x approaches c of f of x and multiplying it by the limit as x approaches c of g of x. So just take L times k. So if I want to do the limit as x approaches c of my f of x function times my g of x function, I can just say, well, what is the limit as x is approaching c of f of x? Well, it's 4. And what is the limit as x is approaching c of my g of x function? Let's multiply those together. -5. 4 times -5 is -20. Okay. The next one is the quotient law, or quotient property of limits. The limit as x approaches c of f of x divided by g of x is the same thing as the limit as x approaches c of f of x divided by the limit as x approaches c of g of x, which is L divided by K, provided that K cannot equal 0. And this is where somebody in class goes, but Mrs. Heiss, well, what if K is equal to 0? Well, then either the limit does not exist or there's another method you're going to have to use. It's not going to have to do with properties. But if all that you're given is this, and the answer for the limit of g of x was 0, then you would just say the limit does not exist. So, we're doing the limit as x approaches c of the function f of x divided by the function g of x. So let's take that limit of the f of x function, which is 4, and divide it by the limit of the g of x function as x approaches c, which is -5. That fraction can't be simplified, so that is the answer right there. Done. Next, we have the power law, or power property, for limits. The limit as x approaches c of the function f of x raised to the nth power is equal to the limit as x approaches c of f of x, just evaluate the limit of that function, and then raise the answer to the nth power, so L to the nth power. So over here, find the limit as x approaches c of f of x raised to the 3/2 power. Well, what is just the limit as x approaches c of f of x that we've been using? It's 4. So I'm going to take 4 and raise it to the 3/2 power. Now, we can actually work that out because one of these numbers is a power and the other one's a root. Do you remember which is which? The bottom number is the root, which is handy because 4 has a square root. Yay! And then the upper number is your power. So what's the square root of 4? It's 2. And what's 2 cubed? It's 8. So the answer to this problem is 8. And the last one, which probably should have been the first one because it's so easy, the limit as x approaches c of a. Now remember back at the beginning, oh, well, I apologize. We should have said let a, b, and c be real numbers. The limit as x approaches c of a, so a is some number, is just going to equal a. So the limit as x approaches 4 of 5 is just going to be 5. This basically means that your function f of x is equal to 5, which means the same thing as y equals 5, which means if you're on your coordinate plane, 1, 2, 3, 4, 5, you have a horizontal line right here. So if x is approaching 1, 2, 3, 4, well, guess where this function it's going towards? It's going towards 5. It's going towards 5 everywhere on that whole horizontal line. It doesn't matter what x value you choose. So when you just have the number after the limit, you're basically looking at a function where y is equal to that number, and it's just a horizontal line, and it's always that number. It doesn't matter what x goes towards. So that's a pretty basic one. Okay, now down here, number 1 says, assume that the limit as x approaches 4 of f of x is equal to 0. And the limit as x approaches 4 of g of x is equal to 3. Part A, what is the limit as x is approaching 4 of the function g of x plus 3? Well, you can break this into 2 limits. You do not have to show this work, by the way. The limit as x approaches 4 of g of x plus the limit as x approaches 4 of 3. And this limit is equal to 3. And then by this constant rule, the limit as x approaches 4 of 3 is 3. So 3 plus 3 equals 6. Done. Okay, the next one is a product of 2 functions. So that means I'm going to do the limit of the first one, and I'm going to multiply it by the limit of the second one. So limit as x approaches 4 of x times limit as x approaches 4 of f of x. Now this first one is one that we could have done in our last lesson on algebraic methods. You can do a direct substitution here. This is the function y equals x. You can just substitute 4 in place of the x, and the output is 4. So 4 times this limit is given up here, 0 equals 0. All right, the next one is using our sum rule, our sum property. The limit as x approaches 4 of g of x plus the limit as x approaches 4 of f of x. These are both given. 3 plus 0 equals 3. Don't you love it when you're in calculus class and your work is like 3 plus 0? If you just write down the answer of 3 for this problem, that is absolutely fine. I don't expect to see all this work. I'm just breaking it down so you can see how it connects to the limit rules that we just discussed. All right, D. Here's a sum. So we're going to split it into 2 and add them. The limit as x approaches 4 of 5 plus the limit as x approaches 4 of f of x. Well, this is the bottom rule, the constant. The limit as x approaches 4, oh, it's the exact same one, wow, 5, plus the limit as x approaches 4 of f of x is given as 0. 5 plus 0 is 5. Okay. I'm wondering if we could maybe do this with showing a little less work on these next 4 since I broke it down all nice on the first 4. Could we move into that next level of thinking, kind of skipping a step, or is that going to be too painful? Let's see, here we've got the sum rule, so I'm going to do the limit of the first one. The limit as x approaches 4 of g of x is 3, that's given, plus the limit as x approaches 4 of f of x is 0, but I have to multiply it by 3 because of the scalar multiple rule. However, 3 times 0 is 0. So we're doing 3 plus 0, which is 3. All right, let's look at next one, F. The limit as x approaches 4 of the quantity x squared plus 4 times f of x. Okay, maybe I'll split this one up for you. The limit as x approaches 4 of x squared plus, remember our scalar multiple rule, we can pull that 4 out in front of the limit, do the limit first, and then multiply the answer times the 4. We want to do that. Now this first one is just direct substitution. Substitute the 4 in place of the x. So 4 squared plus 4 times, what is the limit as x approaches 4 of f of x? That was given to be 0. So 4 squared plus 4 times 0 equals 16. All right, the next one. You think we could do this one without writing it all out with the limits? Just sub in. What is the limit as x approaches 4 of g of x? That's going to go on the top. 3. That was given. What's the limit as x approaches 4 of f of x? That was also given. 0. Down here on the bottom. Minus the limit as x approaches 4 of negative 1. Well, that's that constant rule. So it's just the number. Negative 1. 3 divided by negative 1 is negative 3. All right, now this last one here is kind of tricky because I'm not sure you're familiar with this notation. Do you remember when you were in pre-calculus and you learned the sine of x times the sine of x was equal to the sine squared of x? Do you remember that? Well, this has g squared of x. What this means is the limit as x approaches 4 of the function g of x times the function g of x. times itself. So instead of putting it in parentheses with a square, they just stick it between the function name and the of x notation. So for this one, you take the limit as x approaches 4 of g of x, which is 3, and multiply it by the limit as x approaches 4 of g of x, which was also given to be 3. 3 times 3 is 9. Or you could have used the power property on there and just said 3 squared. That'd work too. Okay, scooting down here to the bottom. These problems are using the exact same properties that we used on number 1, except for instead of starting out by defining the limits for certain values, they're giving us graphs of f of x and g of x, so we kind of have to figure out what those limits are by doing the graphical analysis like we did in our very first calculus lesson. So, part A, the limit as x approaches -2 of f of x. So let's go to our f of x graph. Well, limit as x approaches -2 of f of x. Then we're going to go plus 5 times the limit as x approaches -2 of g of x. So I did the scalar multiple rule, and then we've got this addition separation thing going on. So let's look at our f of x graph. As x gets closer and closer to -2, the y is getting closer and closer to 1. I do not care that that point is there. That point can be there, that point could not be there. It actually doesn't matter what the value is right at -2. What matters is where it's heading on both the left and the right side as x gets close to -2. The y value is getting close to 1. So this is 1 plus 5 times. What is the limit as x is approaching -2 on the g of x graph? So jump over here to the g of x graph. Here's my -2 on my x-axis. What is the y value getting close to here? -1. So -5 plus 1 is -4. Okay. Maybe you could try B and C on your own. Pause the video, give it a try, and then check your answer. Hopefully you have done so. And coming back, we shall look and see. Here we have the limit as x approaches -2 of the f of x graph. Oh, we already did that. It equaled 1. So we have 1 in the numerator. And then the limit as x approaches -2 of g of x, that equaled -1. We also did that one. So 1 divided by -1 is -1. Hopefully you got -1 for B. Part C. The limit as x approaches 1 of f of x. So 1 is right here. What value is the y going close to when x gets close to 1? That would be 2. And then the limit as x approaches 1 on the g of x graph. Uh-oh. Coming from the right, it's going to -1. Coming from the left, it's going to -2. If the left-hand limit and the right-hand limit are not equal, then that limit does not exist. 2 times does not exist. It just does not exist. There is no limit. You can't do it. I want to bring attention to a thing that's up here at the top in the box. These rules can only be applied if the limits exist in the first place. If the limit does not exist for one of those originals, then that limit does not exist either. Okay? All right. Next, we're going to number 3. Number 3 says, use a table to investigate the behavior of f of x equals 3 over x minus 2, the quantity x minus 2 as x approaches 2. So this is bringing us back to the good old lesson 1 of this unit where we did it by tables and graphs. Okay? Now, when we did that on the first day, we used a calculator. And often these types of problems will be found on the calculator portion. However, I would be remiss to tell you that it's always going to be the case because it's not. So why don't we try to do this one without a calculator? Hopefully, since you've had a little bit of time to look over that half sheet of rules about rational functions that I gave you, you probably could figure out a lot of this without needing to use a calculator. So let's see here. I'm going to find the middle of this table, which involves counting, which is the hardest part of math. I'm going to put my 2, the x value is 2, in the middle, because that's what I'm trying to figure out the limit as x approaches. So now I'm going to draw a little graph here, and I'm going to look at my denominator. X minus 2, what number would cause me to divide by 0 here? That would be if x is 2. This is undefined for my table. And how is that going to show up on my graph? Is that going to be a hole in the graph, or is that going to be a vertical asymptote on the graph? Do you remember? Well, it has to be a factor of both the numerator and the denominator for it to be a hole. If it's a factor only in the denominator, that means it is actually a vertical asymptote. So if I go over to, I have a vertical asymptote here on my graph at x equals 2. So let's see. What if I have, oh, and let's see, what about the horizontal asymptote? Is there a horizontal asymptote on this graph? The degree of the numerator, there is no x, it's like x to the 0, and this one is x to the 1, so it's greater on the bottom. So that means we have a horizontal asymptote along the x-axis, y equals 0. Okay, so now I want to figure out what's going on. Where is my graph going? So if I plugged in a 1, positive 1, let's say I put in a positive 1 for x. 1 minus 2 would be negative 1, and 3 divided by negative 1 is negative 3. So when I'm over 1, I'm down 1, 2, 3, right here. What if I sub in a 0? 0 for x. Then that would be 3 divided by negative 2, which is negative 1.5. 3 halves is 1.5, negative 1.5. So 0, negative 1.5 right here. And what if I put in a negative 1? 3 divided by negative 1 minus 2. That's 3 divided by negative 3. Those are like the same except for opposite signs, so that'd be negative 1. So negative 1 goes with negative 1. And what if I put in a negative 2? Well, 3 over negative 2 minus minus 2 gives you negative 4 in the denominator, 3/4, but negative 3/4, negative 0.75. It's going to be like here. So, that's that branch of the graph. Now let's go over here to the right side. What if I substitute a 3 in here? 3 minus 2 is 1. So 3 divided by 1 is just 3. So this goes over 1, 2, 3, up 1, 2, 3, up here. Okay, what if I put a 4 in here? 3 divided by 4 minus 2. 4 minus 2 is 2. So that's 3 halves. 3 halves is 1.5. So over 4 up 1.5. What if I put a 5 in here? 3 divided by 5 minus 2, that's 3 divided by 3, which is 1. So over 5 up 1. And what if I put a 6 in here? 3 divided by 6 minus 2. 6 minus 2 is 4. 3/4 is 0.75. Okay, there's my little sketch of my graph. Here's my table. Now, what happens, what is my limit as x is approaching 2, which is this vertical asymptote, from the left side of the graph? This is going down towards negative infinity. What's happening as the limit as x approaches 2 from the right side of the graph of 3 over x minus 2. It's going to positive infinity. What about the limit as x approaching 2 of 3 divided by x minus 2? Well, since this is negative infinity and this is positive infinity, you really can't say either one of those because they're not the same. So you just have to say that does not exist. Now, would it have been correct to put does not exist instead of the negative infinity? Yes, it would. This is more specific. So this is probably the answer I would be preferential to, because even though the limit does not exist, you're describing why it doesn't exist. It has unbounded behavior in the negative direction. And this has unbounded behavior in the positive direction. So it's kind of giving the reason it does not exist, a little bit more specific of an answer. But it is also correct to say that these limits do not exist. This one, however, you cannot put a negative infinity or a positive infinity or a plus or minus infinity or anything along those lines and infinity at all. Since they're opposite directions, it just has to be does not exist. So notice in the little box here, it says the limit as x approaches c of f of x equaling infinity does not mean that the limit exists. In fact, it tells you how the limit fails to exist by denoting the unbounded behavior. So this is not really a numerical answer to a limit problem. It still does not exist. All right, there's a theorem here. Vertical asymptotes. Let f and g be continuous on an open interval containing c. If f of c does not equal 0, g of c equals 0, and there exists an open interval containing c such that g of x does not equal 0 for all x values not equal to c in the interval, then the graph of the function given by h of x equals f of x divided by g of x has a vertical asymptote at x equals c. This is kind of summing up what we just talked about in problem 3 in really technical math language. Now, the next part here says, how can you use direct substitution to tell you that you have an infinite limit? Well, first, you're always going to try direct substitution. Try to just plug in that number to begin with. And if you plug it in and you get 0 in the denominator, then your next step is going to be, let's try to factor and simplify. And then, after we've simplified, we can turn it into direct substitution problem. Now, if that doesn't work out for you, and in some cases it won't because they won't be factorable or they won't have any common factors that cancel out the problem number, then your next step is going to be to sub in x values on both sides of, let's say, your c value, whatever the number that x is trying to approach, and then make a table, make a graph, and do it like we did up above on number 3. If it's a calculator problem, certainly use the same calculator methods that we learned on day 1, but we've already practiced that. So today I would like for you to practice doing it without a calculator. Yes, it's a little tedious and time consuming, but it's important that you feel confident in your ability to do so without using technology all the time. Okay, so for number 4, can we do direct substitution? No, we end up with 0 on the denominator. Let's try factor and simplify. If you do the limit as x approaches 1, x is the greatest common factor here. X minus 3 would be left behind over x minus 1. Can we cancel out the problem factor on the denominator that's causing us not to be able to use direct substitution because it gives us a 0? No, it didn't work. So what are we going to do next? Well, this means we've got a vertical asymptote here, just like we did on number 3. So if I were to make a little sketch of this thing, it's going to have a vertical asymptote when x is equal to 1 right here. So that means that the limit is going to be does not exist. Bing! I can say that right off the get-go. If I wanted to substitute in a smaller number and a bigger number to kind of get an idea whether I'm going up or down, I could do that. Probably you need 2 numbers on the left and 2 numbers on the right to get that figured out. So like smaller than 1 would be 0. Plug in a 0. 0 squared minus 3 times 0 divided by 0 minus 1. Well, that numerator is 0, the denominator is -1, so that equals 0. So when I plug in 0, I'm at 0. So this is like the origin is a point on this graph. Now what if I went one smaller than that, like -1? -1 quantity squared minus 3 times -1 over -1 minus 1 is 1 plus 3 over -2. So 4 divided by -2 is -2. So at -1 I'm down 2. Okay, so this means the graph's going like this. And then, let's see, do I have a horizontal asymptote? The degree of the numerator is greater than the degree of the denominator by 1, so there's a slant asymptote on this guy. Okay, now on the right side, let's see. Plug in a number bigger than 1. 2. How about 2? 2 squared minus 3 times 2 divided by 2 minus 1. 4 minus 6 is -2 divided by 1. That's just -2. Oh wait, no. 2 minus 1. Yeah, -2. So 2, -2, right down here. And where would my next point be? Plug in a 3. 3 squared minus 3 times 3 over 3 minus 1. 9 minus 9 is 0 over 2, 0. So 0. So this guy is going down on this side. So you can see it's going to positive infinity on the right. Coming from the left. It's going down to negative infinity coming from the right side of the graph. So does not exist would be the only answer you could put here. You can't put infinity or negative infinity on problem 4. Okay, so yes, table and graph method that you have to resort to if direct substitution or factor and simplify followed by direct substitution doesn't work. But really we're substituting numbers into this equation as well, just to the right and to the left of this vertical asymptote to figure out, is it going to positive infinity, is it going to negative infinity, or is it just plain old does not exist? Okay, so let's see, how about this one? Let's try our direct substitution to start. 2 minus 1, 2 cubed plus 2 times 2 squared, that's 1 on the numerator. 8 plus 4 times 2 is 8. This is 1/16. That limit problem is done. Direct substitution is nice. Okay. If we were together in class right now, I would probably divide the class into 3 groups and or split up tables, assign each table to one of these problems and have you try these and then share out with the class. But since we are not, I would recommend that you pause the video, give each of these a try, and then we'll check and see how you did on them. So let's look at, well, go ahead and pause it and then come back. Okay, hopefully you've had a chance to do this. If you try to do number 6 with direct substitution, you get division by 0, so that won't work. So factor and simplify, there are no common factors here. That won't work either. So this is another one like number 4, where you need to make a table and a graph. So here's my little graph. X minus 2 tells me that where x is equal to 2 is my vertical asymptote. My numerator and denominator have the same degree, so the coefficients, the ratio of the leading coefficients is the horizontal asymptote. So that would be 1 over 1, which is 1. So I got a horizontal asymptote here. And now I'm just going to pick a couple points to plug in on both sides to figure out, is my graph up here, down here, up here, down here. And it's going to obviously kind of conform toward it. So let's say I substitute in a 1. 1 minus 3 over 1 minus 2. Well, that's negative 2 and divided by negative 1, which is positive 2. So when I have an x value of 1, I'm at 1, 2 up here above the asymptote. Now, because this is just a vertical and a horizontal, no slant asymptote, you can probably just tell that this thing is going to go toward those two asymptotes from there. Now, let's substitute in a 3. 3 minus 3 over 3 minus 2. That gives me 0 over 1. So when I'm over here at 1, 2, 3, my y-coordinate is 0, which means I'm going to go like this. So as my graph approaches the x value of 2, from the right, it's going to negative infinity. From the left, it's going to positive infinity. So this does not exist. All right, let's take a look at number 7. Let's try a direct substitution here. 1 squared minus 1, 1 squared plus 1, 1 minus 1. Oof. Oh, wait. So direct substitution doesn't work, right? Because we have 0 here and 0 times this is 0 and the denominator equals 0. So we can't do direct substitution. Maybe we can do factor and simplify because that numerator is factorable. Pull out the common factor of x. X minus 1 would be remaining. Woohoo! That is the factor that was causing us problems in the denominator, and it goes away. Now we do direct substitution. So this would equal 1 over 1 squared plus 1, which is 1/2. All right, number 8. The limit as x is approaching 4 from the right side. That's kind of funky. Can I do direct substitution? 4 squared minus 16? No, that's division by 0. Okay, what about factor and simplify? That denominator is definitely factorable because it's a difference of squares. X plus 4, x minus 4. Did we cancel out that problem factor? No, it doesn't cancel. Okay, that means we're back to this make a graph, make a table thing. All right, we have 2 vertical asymptotes here. One at positive 4 and one at negative 4. 1, 2, 3, 4. 1, 2, 3, 4. Vertical asymptote. Vertical asymptote. Do we have a horizontal asymptote? Let's see, the coefficients are 1 for both x squareds. The degrees are the same, so it's the ratio of the leading coefficients for our horizontal asymptote. So that means we have at y equals 1 a horizontal asymptote. Beautiful. Now we just need to figure out where the graph goes. Let's see, what if I plug in 0? 0 would be my numerator, and negative 16 would be my denominator, but 0 divided by negative 16 is 0. So we are going to cross at the origin. What if I substitute in a 1? 1 on the numerator, and then 1 minus 16 is negative 15. Whoa, that's low. Okay, so we're going down toward the asymptote very steeply here, probably more steeply than I can represent on my graph. The negative 1 squared, well, since the negative ones are both squared, it's the same as if you had a positive one, so it's going to be kind of like this. What if I put in a 5? 5 squared over 5 squared minus 16. That's 25 over 25 minus 16. That's 9. 25 ninths. Blech. 9 times 3 is 27, so it's close to 3. Okay, 2 and some change. So that means when I'm at 5, which is to the right of this vertical asymptote, I am at 1, 2, close to 3. So this piece is going to go like this. And now, what if I put in a negative 5? Since they're squared, negative 5 squared is still 25, negative 5 squared is still 25. This is going to give me the same thing. It's going to be up here close to 3, and this piece will go like that. So this is asking me, what is the limit as x approaches 4, which is the x value here, from the right side? Well, that's going to go into toward positive infinity. Positive infinity. Boom, boom, boom. That's the answer. Does not exist would also be correct, but positive infinity is a more specific answer. Okay. Number 9. So, this is just looking at some different scenarios that can come up with your rational functions. The limit as x is approaching c of f of x. Since it's going up on both sides, coming from the right and coming from the left, this one is positive infinity. How about the limit as x is approaching c of f of x here? Since it's coming down from the right and down from the left, we would say that's going toward negative infinity. How about the limit as x is approaching c of f of x here? Well, it's going down, coming from the left side of the graph, and it's going up, coming from the right side of the graph. So this one would have to be does not exist. And how about over here? The limit as x is approaching c of f of x, it's going to positive infinity coming from the left. It's going to negative infinity coming from the right. So this one would have to be does not exist also. Technically, the positive infinity answer and the negative infinity answer could also be represented with a does not exist. Sometimes on the multiple choice questions, they will have just positive infinity, but not does not exist. So you would choose positive infinity. Sometimes they'll have just does not exist and not positive infinity. So you need to be aware that either would be correct. On the first, you could have positive infinity or does not exist. On the second one, you could have negative infinity or does not exist. But you would not be having both of those as an answer choice on the same problem. Okay, the next thing we're discussing is limits at infinity. When we talk about limits at infinity, we're saying now we're not going to make x be a specific number on the graph, on the number line. It's going to say x is going to positive infinity or x is going to negative infinity for some rational function. Or some parent function that you're familiar with, like e to the x or natural log of x. So, this is looking basically at what the horizontal asymptote is. If the degree of the numerator is less than the degree of the denominator, then the function is going to 0 because it has a horizontal asymptote at 0. If the degree of the numerator is equal to the degree of the denominator, then the ratio of the leading coefficients, like say they have an x squared on top and an x squared on bottom, that's the highest degree term for x on both the numerator and the denominator. Whatever numbers are in front of those x squareds, you just make a fraction out of them, and that would be the horizontal asymptote, and the answer is x approaches infinity or negative infinity. It works for either way, left or right. And then if the degree of the numerator is greater than the degree of the denominator, the way you do that is you're going to take your ratio of your highest degree terms of both the numerator and the denominator and look at the end behavior of that function, because the limit as x approaches positive or negative infinity of f of x or over g of x will match the same end behavior as just taking the ratio of the highest degree terms from your numerator and your denominator. That function will be easier to work with. Okay, so a couple other limits that you should pretty much have memorized are for e to the x. Let's see. I'm going to sketch the e to the x graph. You should know this parent function. If you don't, you might want to review it. So here is a exponential growth function, and you can see that if you go toward negative infinity on the left side, it's approaching y equals 0, the x-axis, which is 0. But the right-hand limit, as x is approaching positive infinity, is going up forever. It's increasing without bound towards positive infinity. Now, here is, that's y equals e to the x. Here is y equals natural log of x. It has a vertical asymptote on the y-axis at x equals 0. And it goes down toward it here, and then it curves upwards. It's still increasing on the right, but it's not going up as steeply. It's just rising at a little slower rate. So the limit as x is approaching positive infinity, that's like the right side is going to positive infinity, the left side is going to negative infinity. It's going up towards positive infinity. The limit as x is approaching 0 from the right side here is going toward negative infinity, down, down, down. The y value that it's reaching is negative infinity. Okay, so here are 6 examples using these limits at infinity. Notice every single one of these says x is going to negative infinity or x is going to positive infinity. So we're talking about right-handed behavior or left-handed behavior. So here's a rational function, something over something else. Let's look at the degree of the numerator and the denominator. Degree means the highest power of x. The highest power of x on the top is 1. The highest power of x on the bottom is 2. So that means that the degree of the numerator is less than the degree of the denominator. So if the degree of the numerator is less than the degree of the denominator, then that means this is equal to 0. No work needs to be shown. You just need to know that property. Now, number 2. Again, we have a rational function. X is going to negative infinity. The highest power of x on the top and the bottom are the same. They're both x cubed. So, if the degree of the numerator and the degree of the denominator are equal, you take the ratio of the leading coefficients to be the answer for this limit. So, on the top, the coefficient is 6. On the bottom, the coefficient is 2. 6 divided by 2 equals 3. Okay, for number 3, the limit as x is approaching infinity of 8x to the 5th over 4x cubed. Here, the degree of the numerator is greater than the degree of the denominator. 5 is greater than 3. So, we're just going to take the ratio of the highest degree terms. So, like if this would have had plus 2 and this would have had minus x, we could just cancel those things out. Just look at the highest degree terms and simplify them. What is 8 divided by 4? 2. What is x to the 5th divided by x to the 3rd? You subtract those powers. 5 minus 3 is 2. So 2x squared. Can you picture the 2x squared graph in your head? It's a parabola multiplied by 2, so it's a little steeper, but it goes up on both sides. So as x goes to the positive infinity on the right, this graph is going up to positive infinity. You could also say that it does not exist. Okay, on this one, the limit as x approaches positive infinity of 1 minus e to the x over 1 plus e to the x. So you can break this down. The limit as x goes to positive infinity of e to the x, we just talked about, that's positive infinity. So this is like 1 minus positive infinity divided by 1 plus, again, the limit as x approaches positive infinity of e to the x is positive infinity. What is 1 take away infinity? So I have number 1 on the number line, and then I'm subtracting infinity from it. That's negative infinity. What's 1 added to infinity? Infinity plus 1 is just infinity. Negative infinity divided by positive infinity is equal to negative 1. It's the same value, just one's positive, one's negative. So that limit is equal to negative 1. Okay, on number 5, the limit as x is approaching positive infinity of 5 plus the natural log of x. Well, it's going to be 5 plus, what is the limit as x approaches infinity of the natural log of x function? That's this, positive infinity. 5 plus infinity is infinity, or does not exist. And number 6, the limit as x approaches infinity of e to the negative x. Now this is a little different. This is not e to the x, it's e to the negative x. If you think about your transformation rules, what does that negative do to this graph? If the negative was in front, it would flip it vertically across the x-axis. But when the negative is up there with the x, that's a horizontal flip of the graph. So it goes like this. Flips across, it reflects across the y-axis. So as x approaches negative infinity here, this is the negative infinity side, the y values are going towards positive infinity. All right, I hope that you've had a lot of fun learning today about properties of limits, limit laws, limits at infinity, all this good stuff. Please let me know if you have any questions at all. Send me an email. I will do whatever I can to help you, tutor you, and make sure that you are very confident in your mathematics skills. Have a wonderful day, and I look forward to working with you again soon. Bye-bye.